and welcome to our Advancing Calculus Research and Teaching webinar. My name is Anastasia and I am work here in Marketing Department in Wolfram Research Europe. The topic today will be presented by Joseph Brennan, one of our Wolfram technical consultants. If you experience any technical issues during the webinar, please refresh your browser and rejoin the webinar. If you have any questions, please feel free to log them using the Q&A tab on your screen, and Joseph will answer them while the talk goes on or in the end. Please note that the webinar will be recorded through the Big Marker. If you registered, you will receive the email as a follow-up. If you're not registered, you are welcome to explore our resources in Wolfram U page calendar. The webinar will now begin. We hope you enjoy it. Over to you, Joseph.
Thank you very much, Anastasia. Hopefully everyone is clear on how to navigate the big marker, or possibly some of you are watching on YouTube. Those of you who are here on Big Marker, maybe you can download the notebook and code along with me. So let's get started. As I begin, you may see a couple of surveys. I encourage you to answer these. It just helps us understand who's attending these talks. And yeah, put your questions in the Q&A panel as and when you have them. So we're talking about using Wolfram Language for calculus research and teaching today. I want to demonstrate that Wolfram Language, specifically the Wolfram Notebook interface, is the ideal platform for calculus research and teaching. Okay, so we'll go through lots of examples of different areas of calculus and Wolfram support for them. And I will close out by a section that is not necessarily calculus specific, but it's more general teaching and research. How can you use the Wolfram Notebook? How can you take advantage of the technology available at the notebook level to improve your workflow, etc. Okay. So I want to showcase that the Wolfram Notebook is a complete, highly automated and integrated platform for calculus computation. So I'll go through this summary and talk about what these individual words mean, to me at least, and you should be able to see why we've chosen these words very carefully. So a complete platform for computation. That means that you should have support for all the different areas of calculus. Okay, you encompass all of it. You don't need to look elsewhere for a specific aspect of calculus. Okay, so we have support for that. There's a couple of examples of this here, and we'll go through these in the examples as we progress through this webinar. Now, automated summarizes the goal to reduce human intervention as far as possible. So just going back to this kind of summary slide, that's what we mean by highly automated, okay? Reducing manual intervention. And integrated means you can pull data from various sources and various domains. So maybe you have external libraries or databases or even repositories you want to access. You can do that using Wolfram Language. Okay, for example, something like integrated support for LaTeX comes to mind. Okay, you can format LaTeX in the notebook if you like. I've certainly used this feature a lot. Okay, so the examples are kind of linked to each one of these words: complete, highly automated, and integrated. But I think the examples are, pretty cool in their own right, at just showing what Wolfram Language can do. So let's get started. We'll start with looking at algebraic integrals. Start from the basic and then we'll get a bit more complicated. So those of you who have some background in mathematics should be familiar with this. This is the integral of some integrand with respect to x, and it looks exactly like how you'd write it on a piece of paper, for example. Now, how did I get this integral symbol? I'll show you now. So I'll just open a text cell. This is a Wolfram alpha cell. I'm in a text cell. Okay. So what you want is type escape and then DINTT and then escape. Okay. And then we'll go into this cell and I'll just do that in a code cell this time. So esc. Okay. This gives us a integral sign. We can input the integrand, the integration variable, and the limits. Okay, we can also just use INTT, which means we're going to be integrating without limits. From that, you may deduce that the D in the DINTT stands for definite. Okay, so that's how you get it. However, looking kind of under the hood at this expression, the integral sign is just this typeset form that the Wolfram language interprets. But I'll show you how to get the input form, and you just do Control-Shift-I, and we can see that this is the Wolfram language code that's kind of hiding underneath. So it's just the function integrate with the expression inside, and then the variable with respect to which we want to integrate here. Okay, this functional form or input form is probably more useful because it allows you to type some options in the latter arguments of the function. Okay, this is the one I use. Okay, so hopefully that provided a good introduction to how to calculate integrals in Wolfram language. And here's an example of an integral that was actually unsolvable prior to version 13. And I think that means one couldn't find a symbolic closed form solution for it. But now we can. Okay, so we can run this. We get a long, complicated expression with some square roots and some nested roots and a inverse hyperbolic tangent. So it's actually taking a while, but you can see the output anyway because this is pre-generated code. Okay, here it is. It actually, I think it's found another form of the closed form solution. So that's quite interesting. Just run it again, just in case. Yeah. Okay. So as you can see, the result of this is composed of functions like log in their own right. So this is one of the advantages of symbolic computation, is that you can represent your answer in terms of other symbolic objects. Okay. And partly this is why we say that Wolfram language leads the way in symbolic integration, because it can do this. Okay, having a closed form is useful, and representing that closed form symbolically is also useful because you can then use it for more applications if you want to plot something or visualize something, perhaps. Okay, and there's a link you can follow here for some more information. Here's another example I wanted to share, where we just integrate the exponential of minus ax squared between minus infinity and infinity. And notice how a is kind of blue here, meaning that it's not defined. So let's just run this. Okay, here's the result. It's the square root of pi over the square root of a if the real part of a is greater than 0. So if I hover over this, you can actually see that if you look closely, it's a conditional expression. Okay, this this symbolic object is the conditional expression object. In fact, I just control shifted I on that, and here's what we get. So this is really kind of powerful because it's taken the undefined symbol a, acknowledged that we don't know anything about this symbol, and said, provided this is true, that the real part of a is greater than 0, this would be our answer. Okay, now I'm going to kind of resolve this by uncommenting this, where we input some assumptions into the integral, where we say the real part of a is greater than 0, and we should just get the answer instead of a conditional expression. Okay, so yeah, I encourage you to play around with this and look at or find some integrals that you've maybe seen online, and then see how Wolfram Language does at calculating them. Okay, I'll just check for questions. Adrian has said, can you differentiate the outcome with respect to x and get the integrand as a result? Just to check. Okay, good thought. So we've got this result here. Now, maybe you could copy this and differentiate it, or maybe we could just define this to be equal to some symbol called result, and then differentiate result with respect to x. Okay, so it has differentiated it. Whether it's got it in this nice closed form, perhaps not. It's kind of tricky. It's always a tricky problem to say with definite certainty that two expressions are absolutely the same. One thing that Wolfram Language, especially in the more recent versions, tries to do is get the most simple, the most simplified closed form expression for these solutions. But yeah, this is just an example of me doing this, integrating something and then differentiating the result. So yeah, perhaps this is just too complicated an expression to get nicely back to this. But yeah, good question. Okay, Sam has asked, if we want to see the steps, how can we put this question to Mathematica? Oh, so like a step by step. Okay, this is something that the notebook doesn't have support for directly from the notebook. That you're making me think of a kind of step by step solutions provided by Wolfram Alpha. So I would look there. But yeah, because step by step solutions are very helpful. I think this might be on the Pro account as well. So I'll just put something in the chat now for those of you who are curious. The Wolfram Alpha step-by-step math solver. Okay, and then yeah, Adrian, absolutely. We could plug in a numerical value for x and see if they're the same. So yeah, lots of this is good. Everyone's coming up with solutions even. Okay, Sam has said a couple of other things about guiding the result if you have a table of integrals. Okay, I don't show anything like that in this talk, but yeah, I hope you can find what you're looking for there. Okay, cool. I think we can move on. Yeah, thanks for your questions. I'll do my best to answer them. So let's move on to some showcasing of version 14 and the new functionality in version 14. Okay, so version 14 came out in, I think, January of this year. And with that came the ability to use implicit differentiation. Okay, so those of you who are used to doing this by hand, it's not too complicated, at least for examples like this. It can get very complicated, but doing it symbolically is quite a big step. Okay, so we have implicit differentiation. This is a really cool one. You can kind of show the process here of making a change of variables when integrating. Okay, so we start with a inactive integral. Notice this inactive function. It kind of gives us this, and we hover over and it says inactive integrate. This is an inactive form of the integrate function. Okay, it's been typeset for us and that kind of thing. Now, with this inactive integrate symbol, we can do things like use the integrate change variables. Percent just means the most recent output. And we've made the substitution u goes to tan of x. Okay, and those of you who know your trigonometric substitutions should recognize this is correct. Even the limits have changed, okay? And finally, we can activate the result and carry out the integration with the change of variables, okay? And we get 4/3. So in a sense, we are showing this step by step here, but we had to prescribe the change of variables. So it's a little bit different than getting the step by step solution. Okay. Right. I just put this in as a kind of hint for more if you wanted to look further, but these are, let me go to the documentation. This fractional d is considered a merging calculus operation that I'm not sure how widespread its use is, but this is another thing that came out in version 14 and I wanted to share it, okay? Uh, and this is rather advanced. So those of you who are interested, please um, look out for this kind of thing yourself and read the documentation and see how far you can take it. Documentation is very rigorous and it's very clear. So that should tell you everything you need to know up to the point where you need extensive background knowledge on calculus. Okay. Now, we've seen new in version 14. I actually added something that's new in version 14.1, okay, which came out a couple of months ago. So one of the things that came out in version 14.1 is symbolic treatment of matrices and vectors. Okay. Now, the traditional way to define a matrix is that we have maybe this table of random real numbers that I can show you as a 3 by 3 matrix. Okay. And then I can maybe calculate the inverse of this if I want. But what if you wanted to define M to be an n by n matrix, but you don't want to say what its elements are, and you don't even want to say what n is? Okay. You're being very general here. You just want to have a way of doing the whole thing symbolically. Well, now you can using this matrix symbol function. Okay, so matrix symbol of A represents a matrix with name A. Okay, so we can run this. It gives us a kind of new notation for matrices here. But then what's really cool is that calculating the inverse, so using a function that already existed, inverse, okay, we've been able to calculate the inverse of matrices for a long time. We get a symbolic inverse of a matrix. Okay, and not only do we have symbolic matrices, we have symbolic vectors and arrays of any rank, actually. Okay, so I'm veering away from calculus a bit here, but this should show you that you can perform calculus operations on like transformations of matrices. So this is the quadratic transformation or the quadratic form of the matrix M, and we can differentiate it with respect to the vector V. Okay, so this is just V dot M dot V, and then we're differentiating that with respect to V. Okay, and this is what we get. This is actually known as the vector derivative, which gives the same as grad of V dot M dot V with respect to V. Okay. Also, I've shown some trivial things here, like differentiating V with respect to V. You get a symbolic identity matrix. Okay. If you hover over this, it's a symbolic identity array. Okay, and then what else did I want to show? Um, the chain rule working with matrices and vectors. So yes, this we've taken the symbol M and V. They're both symbols, but they can appear as a head, so the Wolfram language head, and actually defined as functions. So if you have head of x, your M or your V can represent a head, and V of x is a function of x. Okay, this is a perfectly valid thing to do if we're treating everything symbolically. So what we want to do is show the differentiation derivative of the dot product of M and V with respect to x. Okay, this is it. And then this is an example of the chain rule working with matrix and vector functions. So this is M of V of x. Okay, and this gives you just the normal chain rule result. Okay. So Roger has asked, if you ask Mathematica to integrate e to the sine x, you get no answer in 14.1. However, set this question to Wolfram alpha and you get an answer y. Interesting. Okay, let's just check. Can't really think of an idea right now, but it could just be the way Wolfram alpha is interpreting e, for example. Okay, I'm going to ask the same thing to Wolfram alpha. Okay. Yeah, it seems like we're getting another kind of typeset form, but not actually integrating this. I wonder if I used n integrate. Okay, I need to specify limits. Okay, so this works on n integrate. Yeah, I'm not entirely sure on that one. This is a function where numerical integration is more suited to solving. Yeah, I used to know these functions a bit better, admittedly. But yeah, this feels like something you should be able to do with integration by parts. So um, yeah, I'm not sure why it's not showing you the actual result there. Try this again. Just wrap it in evaluate. Hmm. No, I'm not sure. I might get back to you on that. Sorry about this. Yeah, well spotted. Um, okay. But yeah, I I have to move on. There's lots to talk about here. So the next bit is contour integrals. So it's always been possible to um, carry out contour integrals using different parts of Wolfram language, but now we have like this functionality has been packaged up into the function contour integrate. Okay, and this is all part of the um, you know long-term vision to add geometric computation to Wolfram language. Okay, so here's the syntax for contour integrate. We It requires the function to be integrated as the first argument here, and then you have to specify a contour as the second argument. Okay, so this example uses the unit circle. It's not actually the unit circle, it's the circle of radius 4. Uh, okay, the way I'll just show you the drop down here of contour integrate, or maybe the documentation would be better. So we have this Z being a member of some contour, and you might recognize that kind of notation as element. So the way you do that is just escape lm escape. That's how you get that symbol. Okay, so Z must be an element of this contour, and then we just shift enter and run it. Okay, the contour integrate also has an assumed orientation um, along the contour. If that makes sense, but you can change this in the options actually. So I want to open the documentation again, go into the details and options, and you can define some common contours. And I think you'll find somewhere in the options here of the orientation. Yes, sometimes it takes a while to sift through, but it will be in there. Okay. The next thing I'll show relating to contour integrals is a kind of interesting example where we choose a specific contour. Okay. First, let's just show this on a complex plot. Okay, so we define a region in complex space between -5 i and 5 plus 5i, and then we just plot the contour on it and then visualize the function. Okay, so this is just showing you complex plots. It's not actually doing any integrating. So yeah, we've performed the integral and then showed what we're doing on a complex plot. The second example, which is a kind of Pac-Man contour, shows that we can define the function, show what it looks like on a, in a complex region, and then integrate it. Okay, all of this, very few lines of code. I've actually got some plot options here that I've iconized. I can uniconize it. But yeah, sometimes most of your code is taken up by styling options, and you can just iconize it and make it a bit more aesthetic. Okay, I think that's all I wanted to talk about on that front. The next, we're going to look at function properties. Okay, so some of you might have done analysis at university or other. And you know functions have varying properties. And we're going to look at things like multiplicities of poles and that kind of thing, okay? So here's a gamma function that we're going to define and then restrict it to the unit disk on a 3D complex plot. Okay, we've defined a function gamma of z, which just uses the gamma function. Notice the capital G here, but gives it an argument of z cubed minus z over 3 instead of just z. Okay. This is kind of similar to how, we've used complex plot 3D and defined a unit disk here. It's kind of similar to how we defined our contour in the contour integrate example. Okay, so this is our function. We can have a look at this and interact with it. And then this function poles finds the poles of the meromorphic function f with the variable x. Okay, we are actually the second case where it gives the poles of f when x is restricted by the constraints given. Okay, so this is going to give us a list of poles and a list of multiplicities. So the poles are all here. Some of them are complex, some are real, and they all have multiplicity 1. Okay. Here's just another example of function poles in action. So this is a pole at 5 with multiplicity 2 and a pole at -7 with multiplicity 3. Okay. The structure is a bit different because the transpose has taken place here, but this is just a simple example to show you what function poles does. And if you're curious, as always, go in the documentation. Okay, now this next bit is just a verification of the residue theorem for this function. And this is getting a bit advanced, so there's a link here to the residue theorem on Wikipedia in complex analysis. And it states that the integral of a function around a closed loop is equal to 2 pi I times the sum of the residues at all singularities within the loop. Okay, now residue, what do I mean by that? Or what does Wikipedia mean by that? It's a measure of like the behavior of the function near that singularity. Okay, so we're going to calculate 2 pi I times the sum of these residues, and we get this, and then we're going to numerically integrate it using n integrate, and we've got the same. Okay, I wonder if I could even use %66, check that it's true, that this is... Okay, so there's... The reason that's happened is because n integrate doesn't give you a precise thing. So checking that these two things are exactly the same is not as trivial as I first thought. Okay, that's just something that comes along with numerically integrating and approximating. But as you can see, they've returned the same answer. We can be pretty happy that the residue theorem works for this function. Okay. Cool. So maybe someone who's watching has spotted that we actually did a change of variables here. So we changed z to e to the I theta, and then integrated with respect to theta ultimately. Okay. Now that's because I demonstrated integrate change variables before in a relatively simple case, and I think it is considered an experimental function. So perhaps it's not possible to implement this within n integrate just yet. So you have to do it manually here. You have to do a replace all. This is what this slash dot indicates replace all z's with e to the I theta. All right? Okay. Any questions so far? I'm happy to answer them. I'm very happy with the questions I've had so far. Some of them have tested me a bit. It's been a while since I've done some of this content in a academic setting. I'm mostly in my job, exploring other parts of Wolfram language, data analysis, and machine learning, etc. But it's really nice to do a deep dive into one specific aspect, like calculus or like, I don't know, control theory or graph theory or system modeler, for example. So these are all available to you if you have a license. Okay, so let's look at vector variables now. We're still on the complete side of things, but yeah, we're doing okay for time. So vector variables. We've already seen symbolic vectors and matrices, and now we're just going to show an example of how you can work with vector variables. Okay, it's a relatively simple example. We've just got a matrix A and some initial conditions here. And then we generate a solution using dsolve value. Okay, this gives the value of the expression determined by a symbolic solution to the ordinary differential equation with independent variable x. Okay, our independent variable is t. We're looking at some time evolution here. So we just solve this, specifying the initial conditions here. We're actually explicitly stating that x of t must belong to vectors 2, and vectors 2 represents the domain of dimension 2 vectors. All right. If you see some polls coming up on the screen, yeah, just feel free to do those, as I said, and do the survey afterwards too. Okay, so here is, I think this is, I just put this line of code in to demonstrate that dsolve value just gives you the value of the solution, whereas dsolve gives you a kind of rule that x of t goes to 3 cos of t minus 5 sine of t. So yeah, dsolve value is perhaps more useful if you just want to get to the expression. Okay. These functions also exist with an n in front of both of them. That just means you're doing it numerically. And then we're going to plot these solutions, 3 cos of t minus 5 sine of t and minus 5 cos of t minus 3 sine of t, with the plot legends being just string expressions of the functions themselves. Okay, and then we can actually plot them together on a parametric plot as t goes from 0 to 2 pi, and we have a circle with radius equal to the magnitude of the initial conditions, which is what you'd expect here. Okay, so that was a quick example. Now we're going to look at special functions here, and I touched on it at the start. When you compute something and the answer that you got is actually composed of other functions, and we saw one with a hyperbolic tangent and we saw one with log, etc. This example delves a bit deeper into that and says you can represent the solution in terms of, very specialized, quite complicated functions. So let's see. So we're going to use dsolve value on this differential equation. And with respect to x, okay, we want a solution for y of x, and here it is. So we have a couple of exponentials in here. We've got undefined symbols a, d, c, and b. And we've got some constants of integration that appear as well. But I want to draw your attention to the Hewn C function. Okay, so I'll bring up the documentation of this. Hewn C is its own function in Wolfram language. And this is its definition. It satisfies the confluent Hewn differential equation given by this. Okay, now what's happened there is that, the Wolfram language kernel has found the solution and determined that the simplest way to give the solution is in terms of these Hewn C functions, which is really quite powerful. Perhaps if it didn't do that, we'd be looking at something completely unintelligible. Okay, and then this next part is just showing you how properties of the Hewn C function and other special functions are built into the language, so you can explore those individually if you like to. So here's a series expansion of the Hewn C function as z goes from 0 to 3. Yeah, you can see the function series generates a power series expansion for f about the point z equals 0 to order 3. Okay, yeah. And then we just have terms of order 4 on the end here. Okay, this next part takes some values of alpha, gamma, delta, epsilon, and then evaluates a family of Hewn C functions with the parameter actually varying. Okay, so I'm going to pay very close attention to the syntax here. Alpha, gamma, delta, and epsilon, they're defined. Okay, we have a list of 4 things, setting it equal to another list of 4 things. Okay, that they're going to be element-wise equal to one another. So they're sorted. Q and Z can vary. Okay, and notice by the turquoise coloring here. So inside the table function, that's where the Q is varying. So that's varying from -8 to 8 in steps of 4. And then Z is actually what's being plotted. Okay, so we're plotting the function against Z, but Q is being allowed to vary. So Q is what generates the family of functions, Z is what generates the plot. Okay? And here we are. You might notice a cutoff. We never actually reach 1 here because this specific function has a kind of discontinuity at 1. Which causes an issue if you want to plot it. Okay, so next example. Here we're going to look at partial differential equations, all right? And we're going to consider a Clairaut equation. So we've kind of looked at this already, looked at how to make the typeset form of the integration, but the partial differentiation is, the way you do that is with escape, PD, escape. Okay, so I'm just going to make that now. And the way you do subscripts is just control underscore and then your subscript. All right. So we use these in this example. So here's our Clairaut equation. You can have a look on the Wikipedia if you like. So we're going to define that and solve it, giving a 2-parameter family of planes, okay? Because we have 2 parameters, C1 and C2. Okay, and then we're going to take our u as a function of x and y and replace all with the first of this family of solutions. All right. And that's because a list of solutions are returned here from, yeah, so first, it's not that there's more than one, it's that this has returned a list of functions and there's only one that we need. So we just have to use first to kind of take the only solution there. Okay. So I'll just show you what first is doing. Okay, it's just kind of removing this outer set of curly brackets. Okay, so we've got our two parameter family of planes, and then we're going to set one of these parameters equal to -1 using another replace all. Okay, so now we've got C2. C1 is the only variable that we're allowing to take on multiple values. Okay, and then we solve the family of, well, we solve the partial differential equation for C1, and we just get C1 goes to -x. Okay, then we have an envelope of solutions, and we can visualize these solutions using a manipulate, actually. Okay, so watch what happens as I vary n. We actually see the plane kind of trace, or is always kind of tangent to the envelope of solutions. Okay, now I should specify n is just what we're allowing C1 to be. Okay, so there's quite a few steps there, and admittedly, I don't need to go into all of it. But if you take a backward step, what we've seen there is a lot of replace all, um, finding solutions that have multiple parameters. And then in our investigation, we're kind of fixing one and exploring how um, changing the other affects the solution. Yeah, so this solve, what it did is simply find the envelope of this family of planes. Okay, it's quite an informative, interactive result in the end. Just going to check for questions. So, someone has asked, does Mathematica handle hyperelliptic functions? So, this is perhaps getting beyond my knowledge, but I have found a resource function in the Wolfram function repository that is called hyperelliptic ODE. Okay, so if you're interested, I can put this in the chat and hopefully you find it useful. So I guess what that's saying is that there may not be a function built into the core language that handles hyperelliptic functions, but someone has obviously found a use case for making a resource function that does. Okay, and this, if you have a look there, it gives you a good insight into um, the function repository and how that's just a kind of l- repository of functions made by Wolfram power users who think there ought to be a function that does this, so let me just make one. Okay, some really interesting stuff on there. Okay, so this next example, we're going to look at a one of the challenges that was in the $100 100-digit challenge problems. Okay, this will take you to another Wikipedia site, and it was 10 problems in numerical mathematics where a $100 prize was offered to whoever produced the most accurate solution. Okay, I think 10 significant digits was all you need, and because there are 10 problems, that's 100 digits in total. I think that's where the name comes from. Okay, so this integrating this was in fact on this list. Okay, this was the early 2000s. But we can actually integrate this numerically just in one line of code. Okay. So I made the joke last time I conducted this webinar that unfortunately they're not giving out $100 anymore. Um, okay, and then we can plot this function, visualize its behavior. It's highly oscillatory. And this is actually a kind of erroneous test here because some methods, when you give them to n integrate, actually fail. Okay, so the double exponential method, when you specify this explicitly in the n integrate options, will fail to converge and then just give you a kind of nonsense answer. And then this is another example. If you prevent the Wolfram kernel from doing any symbolic analysis, it also gives you a completely wrong answer. Okay, so I suppose what this shows is that yes, you need to be careful when specifying methods. Some methods may give you wrong answers. Some may be the ones you want. And in this case, you need to let the Wolfram kernel do its symbolic processing. Okay. So this has kind of disabled the kernel from treating the integrand symbolically in any way. I'll just open up the options and details for an integrate, and you can see the extent of the options here. So these are some possible explicit settings for the method option. You can actually have sub methods as well. Yeah, it's very well documented and it's quite far reaching. Okay, so those of you who are just joining, these errors are deliberate. They are just showing that under certain constraints, you won't get the right solution. But just um, with no specified method, it finds the correct answer. Okay. I think there's one other example I wanted to show from the integrate documentation. Sorry. It's this option called evaluation monitor. Okay, I'll show you this. So look at these options. Evaluation monitor is one of them. I can jump to the example that uses it, and then I'll just copy this code and paste it in the notebook. Okay, so there might be a bit of unfamiliar code here, but what this is in principle showing is it's how the integrate function is choosing to sample the integrand in order to perform the integration. Okay. So we see different plot points at different kind of sampling levels, you could think. And Evaluation Monitor, I believe, has its own may have its own documentation page. Yeah. Okay, this is an option for various numerical computation and plotting functions that gives an expression to evaluate whenever functions derived from the input are evaluated numerically. Okay, so you can use this as an option in many different things. This is just an example of it being used as an option of, numerically integrating 1 over the square root of x. Okay. So this next part, we're going to again look at partial differential equations, and it's kind of a fun example, and um, it, the title here is Convenient Real World PDEs. I'm not sure how real world ultimately the answer we derive here is, but I've certainly used similar functionality to this, to like Laplacian eigenmodes, eigensystems, and simulated the evolution of waves on a lake, for example. It's really cool what you can do. But yeah, what we're going to do is solve a Laplacian, generate some eigenmodes, and then pick one eigenmode, and then essentially visualize the behavior of that eigenmode on a region of our choice. Okay? There's a reason I picked this for the integrated example, because we're kind of pulling on lots of different um, pieces of functionality here that are all integrated in this notebook interface. Okay. So we consider a 2D Laplacian term, and hovering over this, we actually see that it's an inactive div operator. Okay. Now, ND eigenvalues, this will give us the n smallest magnitude eigenvalues, so we want the first 5. And notice here we've given x and y as being members of a regular pentagon. Okay. This is what regular polygon 5 is doing as our region in this example. Okay. The symbol V, I think, was from before when I was using vector symbols. So I'm just going to clear it and run this again. Okay. Here we are. And then, yeah, this is the more interesting example here. So this image is just a binarized image of a swordfish or something. We're going to use the function image mesh, which converts an image to a boundary mesh region object. And we can actually use this boundary mesh region to specify our domain for ultimately solving the eigensystem. Okay, notice the region is inside this function ND eigensystem. Okay, so we're going to solve the Laplacian for the 10th eigenmode. This part is just taking the second. Well, let's just remove this and see what we get. Sorry, I'll just run this again. Perhaps there's a reason you specify a you specify that you just want the 10th eigenmode here, but I'm just going to have to define these again. Sorry, everyone. Here are, yeah, I think there was an issue before with some things being defined earlier. So here are the first 5 eigenvalues of the Laplacian in a regular pentagon. And then we're going to try this again. Okay, good. So this returns the eigenvalues and eigenfunctions in a list, or in a list of lists. One list contains the eigenvalues and one contains the eigenfunctions. Okay, we want the 10th eigenfunction. So, quick test. You want the second list or the second sublist, and you want the last element. Okay, hence 2 minus 1. Okay, and we're back to where we started. Okay, sorry about that. And we're just going to visualize this interpolating function on a 3D plot here. Okay, so this has been pre-generated. So this is kind of projecting the 10th eigenmode onto this boundary mesh region specified by the image of the swordfish. Okay, so kind of crazy, but a nice complete example of taking something as simple as an image, okay, a binarized image. The image didn't have to be binarized. We could have used the function, binarize, to binarize another image if you just had a image of a swordfish that wasn't black and white. Okay, so it's just drawing on those external data sources that I wanted to showcase here. Okay, so that's the end of our example. So I'm just going to check questions. So Loris has said, for the integral of e to the sine x, they obtain the same result as Wolfram alpha if you compute with Mathematica this. Okay, so this could be a way there. I think this is okay. I think this is the same as what you had. Can you, if you could confirm that, that would be great, because all I've done is just copy your code from the chat. But yeah, this is what we've essentially done there, is integrated the series, the power series corresponding to e to the sine x. But certainly more informative than what we had before. So thank you. Okay, so for anyone else who was confused on that example, hopefully that helps. In fact, it's funny to think about these things. My first exposure to Wolfram Language was watching a YouTube maths professor calculate some integrals that apparently Wolfram Alpha couldn't solve. So, yeah, this was many, many years ago, but this is how I first was exposed to Wolfram Alpha as an integral solver and search engine for computation. Okay, so we can now start to talk about the needs of research and teaching and how they relate, and how, yes, and how we have support for all of these. Okay, I just wanted to summarize actually with the I've just typed in this to Wolfram Alpha, and there is no indefinite integral for this result e to the sine x. Okay, so that's what it's concluded. There's just no closed form, so that's why you have to resort to doing it in terms of a series expansion. Okay, so whilst that may not be satisfactory to everyone, I think there are just some functions that you can't calculate an indefinite integral for. Okay, right. I digress. Research versus teaching. So I've demonstrated how you can essentially use Wolfram language to teach, hopefully in this hour and a half webinar. And maybe some of you will go away from this and do your own research using some of the functionality you've seen today. Okay, now the message is really that the needs of research and teaching are very similar. Okay, you want to spend less time on the implementation of solving your problem and more time on actually solving your problem, if that makes sense. This is kind of bringing in the broader ethos of Wolfram language as a tool. Okay. I also want to emphasize the clear presentation of ideas. Okay, so the, things like the typeset integration format and the ability to use images and seamlessly integrate like audio, video, images into the notebook. Okay, these are things that are incredibly useful whether you're a researcher or you're teaching. Okay, and this is a specific deep dive into the Wolfram notebook. So what's amazing about the Wolfram notebook is that computation, interaction, and narrative can all take place in the same platform. All right. The code, even if you don't know any Wolfram language, I'd like to think it's relatively short and human readable. Okay, because the functions correspond to real words and um, real life operations. So you should be able to kind of at least um, tell what the code is doing. Okay, even if you don't know the intricacies of the code. Okay, so we've talked about these. We have a large language model integration, which I will show a little bit of. Uh, these are all reasons why we think that Wolfram notebooks are the ideal teaching platform. Okay, and then we'll talk about different modalities for teaching now. So this is a reminder that this whole thing has taken place inside a notebook. And there's opportunities for self-learning. Okay, if you perhaps happens more often than I thought, is that people release kind of the notebooks corresponding to actual textbooks. So if you follow this link, it will take you to this page of a calculus textbook that actually is available both as a hard copy and as a computable notebook format. Okay, you can also embed lectures into your notebook, and the Wolfram U website has many courses that you can take on lots of different areas of Wolfram language or computation more generally, and the kind of question answer aspect of those courses all takes place within cloud notebooks as well. So okay, this is all happening in the notebook interface, whether it looks slightly different because it's in the cloud. um, it's all the notebook interface. Okay, moving on. This is relatively new development, and whilst this talk is not about AI and large language models, I always like to show it. So I can use this function create notebook with the and specify that I want it to be chat enabled, and it will open a notebook for me that has this chat box. Okay. Now I can, because I've connected my Wolfram account with an OpenAI API key, I can call on this LLM. I could have chosen a different LLM. So lots of other LLMs are available. You can see them all here. This tick next to OpenAI just says that my account is configured with them. Okay, so let's just start simple. Let's just say hello. Hope for a response. Okay, what is monotonicity? Here we are. Okay, so I could ask it to, explicitly look at my code and tell me where I went wrong. But this is just example of general questions as well that you might you might want to just go directly to the LLM, but I would really stress that if you can give your LLM access to your code and kind of equip it with the power of Wolfram language, it's a lot more effective. Okay. We also have these LLM functions, which kind of, well, the best way to illustrate this is with an example. So this is a function that has been defined, and these backticks kind of indicate that this is an argument to this function. And we've just run this function with the person being given the value of Albert Einstein. So what this is really doing is asking an LLM to tell you an interesting fact about Albert Einstein, but we've left the person as a kind of argument that could be any person. Okay, so there you go. Interesting fact. Okay, I just wanted to see in the chat, Sam has said it is very similar to having a room full of cooperative clerks to verify and test a variety of problems. Fabulous. Yes, great summary of a Wolfram Language webinar. Thank you very much. It's nice when I have people in the chat. Actually, I much prefer it when I don't feel like I'm talking to no one. Okay, where was I? This part of the webinar, it kind of offers you two sides of the coin of exploring a new topic, and it says constrained exploration or open-ended exploration. Okay, so what comes under the constrained exploration side of things is perhaps looking at a very specific Wolfram demonstration. So this demonstrations.wolfram.com is really such a good resource. Okay, I encourage you to go there and look at the calculus options, look at the physics options, look at the sociology or finance option examples, right? There are over, I think, 13,000 different demonstrations. Yes, that's right. So here's the main site. So this is code that people have written, and they think that it makes it a fun, informative demonstration, and you can interact with that demonstration. Okay, so this is a multivariable derivative test, and I've actually hidden the code, but it's here, and I can run this, and then I'll just hide it again because it is a bit long. And as you can see, that there's lots of different functions we have just at our fingertips here. We can click through these, vary the height of the curves, vary the Z height, use a different kind of surface mesh, that kind of thing. I mean, without going into the specifics of the demonstration, um, I'm not entirely sure what this is showing you, but this is just an example, and it's a very interesting one. I mean, just to have access to all of this in not many lines of code, and you can just go onto the Wolfram demonstrations and either download the source code or just play around with it. So here is a link to some calculus demonstrations. Okay, so that would be if you want to deep dive into a very specific topic, but if you wanted to do a more open-ended exploration, Wolfram Alpha and natural language querying is your friend. Okay, so here's just a simple bit of code that if you wanted to create this, you'd have to know, the syntax, you'd have to know the options exist, and you'd have to know how options worked in Wolfram language. But let's say you just want to ask Wolfram Alpha the same question. It will just generate the code for you and generate the output of that code. Okay. The way you get this Wolfram Alpha input cell is you open a new cell and press equals. Okay. If you want a Wolfram Alpha long input cell, you type equals equals, and then you have this spikier logo here. Okay, so this is an example of this longer input just on the function sine of x, and it will pretty much just tell you everything it knows about the sine function. Sometimes I think this will never end. But you might be able to tell this is open-ended, right? The prompt was just sine sine of x, and we have all of this. Okay, and there seem to be some Wolfram Alpha users in the webinar today, so that's great to see that people are using it. Okay, here's a more specific question and step-by-step solution. So someone mentioned this before. So this gives some step-by-step solutions of if you want to find some global minima or maxima. But then we also have a link to some examples that have step-by-step solutions. Yeah, so it's kind of a repository of examples. Okay, in all different areas of mathematics here, and here's the calculus section. Okay. The next part, the next modality for teaching is a computational essay. Now, I think the real power of this is that you can have, lines of code interspersed with text. Okay, so you can write your piece of code and then talk about it below. In fact, if anyone doesn't already know, well, I'll first show you an example of a computational essay. And it is in fact one of Stephen Wolfram's writings on what is a computational essay. So, there's code interspersed with text here. That's all it is. But it's really powerful because, especially in the Wolfram language, when your code is readable as well, however readable it is, you can always talk more about it when you kind of expand upon your ideas. So that's what these computational essays try and do. And every one of Stephen Wolfram's writings is actually its own computational essay. Okay, this one came out yesterday on the nature of time. Okay, and all of these figures, pieces of code, they will have code attached that generated them, which is really quite powerful, I think. Lowers the barriers to entry for, quite complicated topics. Okay. Now, building on the idea of computational essays, you can deploy content to the Wolfram cloud using this cloud deploy function. So this actually, say you've written some code, this leaves the code as executable. So anyone with a Wolfram ID, which is actually free, because you can have a cloud account and maybe you have a free trial or something, they can run the code you've written and then interact with the content. Okay, just cloud publish. So we have cloud deploy, we have cloud publish. This is a bit different than cloud deploy because it's you can't execute the code. You can just see what's there. Okay, but that's why cloud deploy is very powerful. And we have lots of webinars on this kind of thing if you're curious about sharing your code with others or sharing apps that you've made, or that kind of thing. Okay, and then we're about coming to the end now, so I just have lots of different tools that you can use, such as these author tools, and then there's a bit of a where to go next on the final slide. But in conclusion, I'd like to think that Wolfram Language has been demonstrated as a complete, highly automated and integrated tool, the ideal platform for research and teaching, and an ideal platform for calculus computation as well. So thank you for your attention. I'm just going to stick around for some questions if you have them, if you want me to clarify something or check with me that some functionality exists that you're interested in pursuing. But while I'm waiting for questions, I will leave this slide up, which is an invitation to come to our next webinar on building a data science pipeline at the end of October. Here are those next steps I talked about here. Free trial of the Wolfram language, and then some links to these Wolfram U courses. All right, thank you very much, Hector. Yeah, if people are starting to leave, you feel free to go if you have no questions. If no one has any questions, I'm happy to just end it 5 minutes early, but I hope you found it useful. And yeah, I have a suggestion here on organizing a seminar on a different aspect of Wolfram language functionality, which is control theory. So yeah, well, happy to take your suggestions. Thank you, Saran. Thank you, Amit. Yeah, thanks everyone for coming. I'm going to end it here. All right, bye everyone.